Rochelle, you need to unmute yourself.
There's a story actually attached to this. I think it was February the 12th. It's a Friday morning. I was listening to LBC and I heard Professor Smith being interviewed by Nick Ferrari. And it was such a fascinating interview that I decided that I wanted to find out if I could ask Professor Smith to come and give a talk to Kenton. Well, it took quite a lot of detective work actually, because first of all I contacted LBC and I didn't really get any response. So then actually I contacted another professor of science, and that eventually led to finding that Professor Caroline Smith was based at the Natural History Museum. I then sent her an email and eventually I got a reply, but after that I didn't receive any response, because the security system on the computers at the Natural History Museum are probably better than they are at Westminster. Anyway, here we are this evening for a very interesting talk to be given by Professor Smith and Dr. Keyron Hickman-Lewis. And Professor Smith obtained her first degree in geology from St Andrews University and her PhD in planetary science at the Open University, and she's had a post-doctoral fellowship at the Natural History Museum and the University of Glasgow, returning to the museum as the Meteorites Curator and now head of Earth Sciences collections, and the 10.5 million specimens and objects and a team of 30 curators who care for them. And the main interests are mineralogy and petrology of the meteorites. And Professor Smith is a member of the Mars 2020 mission science team working with the Sherlock Instruments and Science team. And she's Honorary Professor of Planetary Science at the University of Glasgow. And Dr. Keyron Hickman-Lewis had masters at Oxford and PhD in a joint program with Orléans University and Bologna. And he is presently the UK Space Agency Aurora Research Fellow at the Natural History Museum. And the research is focused on understanding ancient fossil traces of microbiological life and their environment, mostly using the rock records of South Africa and Western Australia, and currently he is the return sample science participating scientist on the NASA Mars 2020 mission, where his role involves participation in day-to-day mission operations and helping to define and rationalize selections of samples for return to Earth in 2030. So it's a great pleasure to introduce our guest speakers this evening.
Thank you very much for that lovely introduction, Rochelle. And yes, we do have some very interesting security systems on our emails at the museum, which either let in all types of spam, including various things that it shouldn't be letting in, or indeed nothing. So it basically goes from one extreme to the other, and there's no rhyme or reason for it. But I'm actually going to be in charge of the computer for the first bit of the talk, because Kieran's going to be talking. So we've had a bit of a try around with Zoom and sharing control of the screen. It didn't work very well, so we're going to go old school. So Kieran's going to say, next slide, please, to me, and I'll hopefully be able to do it. So please do bear with us as we go through this. If there's any technical glitches, we'll try and get through them as quickly as possible. And hopefully Maurice might be able to come in with some words of wisdom if we get stuck. But I will hand over to Keyron now, and hopefully you can see there's the Rover, and there's one of the very important instruments, one of the cameras there looking at the Ingenuity helicopter. But I'll put myself on mute now and ask Keyron to start the talk. Thank you.
Okay, so thank you very much all for inviting us here to speak with you this evening. Over the course of the talk, we'll discuss some of the aspects of the Mars the 2020 Perseverance rover mission, what it's searching for, its objectives, and some of the perspectives for the future when these samples will be returned here to Earth for further studies. So as Caroline said, on the screen you can see the rover and the helicopter currently in operation on Mars. So over the course of the talk, we'll speak a bit about the mission itself, what are its objectives. We'll also talk about the landing site on Mars, Jezero crater, and how to go about choosing an appropriate landing site. The main objective of the mission is to understand the geology of the landing site and to understand the potential for traces of a fossil life at the landing site. So this is a field termed astrobiology, which is the search for the distribution and the nature of life in the universe. We'll also talk a bit about the science that the rover will be undertaking during its operations on Mars and how it will be preparing for Mars sample return. As was mentioned, we are actively working on the kinds of considerations to understand which samples we need to bring back for further analyses here on Earth. So that's called returned sample science, and we will finish with a discussion of some of the planetary protection aspects once the samples have been returned to Earth. Next slide, please, Caroline. So it seems hard to believe, but Perseverance launched almost 1 year ago. It launched on July the 30th, 2020, and after a journey of about 7.5 months, it landed at the surface of Mars on February the 18th, 2021. So we've been in operation for around 4.5 months at this time. The current Mars day is day 130. On Mars, we don't talk about days, we talk about sols. So a sol on Mars is approximately 40 minutes longer than a day on Earth. So every day there's a slight shift in the time between Earth and Mars. We'll talk more about that a bit later on. Next slide, please, Caroline. So on its 7.5 month journey to Mars, the most exciting part is of course when it arrives, and the rover was equipped with a whole suite of cameras that imaged its descent through the Martian atmosphere, and this is often called the 7 minutes of terror, because you have these minutes of no communication as the rover descends through the atmosphere, and you only know it's just safely arrived after the fact. So the cameras on the rover were able to image some of the very exciting stages of the descent. So here you can see the release of the heat shield, many hundreds of kilometers above the Martian surface, tens to hundreds of kilometers above the Martian surface. If you could go on, please, Caroline. As we approach the surface more closely, we begin to see some of the topographic features. So the feature you can see at the right-hand side of this screen are the delta sedimentary deposits that are one of the prime targets of the mission. You can also see some of the craters which were used as tools as a waypoint to control the descent of the rover. If you can go on, please, Caroline. As we approach the surface, the rover deploys hydrazine rockets, which help it to slow down just as it approaches the surface, because the rover has to slow from several hundred meters per second in the upper atmosphere of Mars to only 2 meters per second as it arrives for a soft landing. So here you can see the effect of the rockets blowing away dust and sediment at the surface of Mars. If you could go on, please. And there were also wonderful images taken of the parachute and the landing apparatus, which is called which is termed a sky crane, because of the way it lowers the rover out of the sky. If you can go on once more, please. So here you can see the sky crane itself, and you see the ropes connecting the crane to the rover, which is currently being lowered onto the surface of the planet. You can also see a communication cable, an electricity cable between the two. If you go on once more. So when the rover is deployed, the sky crane flies away, and as you see in the following image, we were able to see even the crash site of the sky crane a few hundred meters away from where the rover landed. So this basically takes you through the complexity of the landing process. It was the first time that the landing process had been recorded, and if you haven't seen the videos of the landing process, I would strongly advise you go to take a look at these, because they are tremendously impressive. And on the next image, this was actually taken by one of the orbiters around Mars at the moment, and you can see floating down through the atmosphere is the rover with its parachute. I believe that this image is taken at a distance of approximately 400 kilometers, so it's a real testament to the magnification and the resolution of the camera that took this, that you can see it serenely drifting down through the atmosphere on its journey to the surface. If you could go to the next slide, please, Caroline. So now on the surface of Mars, Perseverance joins a growing fleet of rovers and landers. This year in particular is a significant year for Mars exploration, and there are three missions sent to Mars. There's, of course, the Mars 2020 Perseverance rover. Then there is the United Arab Emirates Hope orbiter, and a third mission, the Chinese Zhurong rover, and a lander joined Perseverance on the surface a few weeks after. So I think there's a bit of a traffic jam at Mars at the moment. It's an uncommonly busy period on the planet. Also, the Curiosity rover, which has been in operation since 2012, is still gathering data. The Perseverance rover has as its prime objective detecting traces of fossilized life and reconstructing the environment at Jezero crater, the landing site in the distant past. And indeed, these rocks come from an extremely early part of Earth history. They are more than 3.5 or 3.7 billion years old, so that's 3,700 million years old. And it's during this period of early Mars history that we believe the planet could once have hosted a biosphere. If you could go on to the next slide, please. So in terms of choosing a landing site, there's a whole planet to choose from, and there are many compelling targets. So why go specifically to Jezero crater? There are a number of reasons for this. The first is that Jezero has an extremely diverse geology. You have sedimentary rocks, you have igneous rocks, you have potential chemical deposits, and also deposits reworked by impact events. So in Jezero, we assume we have a wide range of environments, which makes it a very interesting place, geologically speaking. One of the main reasons is that these rocks, as I just mentioned, were deposited very early in the history of the planet, and it's thought that this is the period of Mars history during which Mars may have been habitable, and therefore is a good target for astrobiology, the search for the nature and distribution of life in the universe. We also have a number of sedimentary environments or sedimentary rocks that were deposited under the action of water. Now, canonically, here on Earth, we know life is associated with water, and the mantra for life detection elsewhere has long been to follow signals of water. So we know we have lake deposits. We know we have a delta deposit, perhaps not dissimilar to the Mississippi Delta on the modern Earth. We also know we have river channels. So these are unambiguous water deposited sedimentary rocks. And as a final point, many of these aqueous settings, many of these water-driven settings, are very similar to those of the earliest fossils we have on Earth, and therefore we believe that the ancient fossil record here on Earth can be used as a kind of comparative tool, as a kind of analog for understanding what life might be like elsewhere in the solar system. You can go on to the next slide, please, Caroline. Okay. So around Jezero crater, as I mentioned, we are currently here on the red spot. That is the current location of Perseverance around Sol 130. So we are currently on the crater floor. In the coming months, we will be exploring some of the units, both igneous, volcanic, and sedimentary on the crater floor. We will hopefully have an opportunity to explore some of these delta remnants, which are relict portions of the delta, which you can see as the major feature in the middle of the image. Probably in about 1 year's time, we will make our way onto the delta, and we will analyze some of the very fine-grained sediments in the delta, which may have very good potential for preserving fossils if there was ever a biosphere on Mars. And in about 2 years' time, we will make our way to the margin of the crater, and you can see these crater rim deposits and carbonate rocks also, which are very useful for reconstructing past environments in the crater. After that, the rover will drive out of the crater and embark on the second part of its mission, which is outside the crater to the west, where it will analyze some of the oldest rocks at the surface of Mars. And we have tools to help us understand the changing geology and how to plan our route through the crater. So this colored map is a combination of images of the surface and an overlay of the estimated rock type. So this is a kind of map called a photogeological map. So we can see Perseverance is here, and at the moment we're in the red region, which is the crater floor deposits. We will probably follow a path quite similar to the black dotted line, meaning that we will explore the delta, then some of the carbonates at the rim, and then head out for the extended mission, for the second part of the mission outside of the crater. And as we mentioned, one of the major objectives of the mission is to collect samples which in the future will be brought back to Earth. So you can see a small point in orange at the left-hand side of the screen which says cache. And this is one of the proposed locations for dropping off some of the samples collected during the mission, where they may be recollected in the future and brought back here to Earth for future study. So in the past, Jezero crater, and indeed Mars, wasn't the dry and inhospitable world we know today. We think that Jezero crater hosted for possibly many millions of years a lake system, and the delta deposits we see now represent the inflow channel into this crater. Now, many of the rocks in the delta, many of the sedimentary rocks are extremely fine-grained, and we know from rocks here on Earth that usually means a high potential for preserving organic materials, and potentially a high potential for preserving traces of biology if a biosphere ever emerged on Mars. And in many ways, understanding the early Mars can help us to understand the early Earth. We think early in their histories, the planets had very similar trajectories. They both hosted bodies of water. They both hosted extensive volcanic processes. So although here on Earth our rock record from the earliest history no longer exists, it's been destroyed by plate tectonic processes over the course of billions of years, it is possible, and indeed probable, that as we find ancient rocks at the surface of Mars of this age, about 3 to 4 billion years ago, this can help us to better understand the history of our own planet. So there are many reasons for visiting Mars, and indeed specifically for visiting Jezero crater, in terms of understanding not only the history of the planet, but also the wider history of the solar system. If we could go on to the next slide, please, Caroline. So for selecting the landing site, this is an extremely long process. I think often many people don't realize the debate that goes into choosing the landing site. For Mars 2020, this took more than 3 years, and there were multiple meetings called landing site selection workshops, at which people can present the case for a specific landing site, and these can be debated and discussed amongst scientists and together with the mission project science team and NASA itself. So originally there were 8 candidate landing sites spread across the surface of Mars, of which 3 were selected for a further study, further consideration. And after 18 months of further consideration, in 2018, Jezero was announced as the landing site. So here are the 8 sites that were selected, spread out across some of the most ancient rocks at the surface of Mars. You see the 3 in the boxes: Northeast Syrtis, Jezero Crater, and Columbia Hills. These were the 3 selected for further consideration, of which Jezero was the eventual selected site. And in the further consideration, most of the discussion surrounds orbital information taken by orbiters, satellites that are currently orbiting Mars, or were at the time orbiting Mars. So these gave us information about the geology of the landing site, and these gave us information about the preservation potential for biosignatures at the surface of Mars, because, as I mentioned, astrobiology is the primary goal of the mission. Go on to the next slide, please. So some of these orbital imagery include high-resolution images, mostly taken by the Highrise Camera, which is the same camera that took the image of the rover descending through the atmosphere. So here we can see topography at the surface of Mars. We can even see individual rock outcrops and get an idea of some of the geological diversity. And this helps us to understand whether the site is a safe landing site for the rover. And we also have chemical information from instruments such as CRISM, which is orbiting Mars at the moment, and this helps us to understand the geological and chemical diversity of the landing site in greater detail. So understanding all of these factors together helps us to make the best choice for a compelling landing site for the rover. And it's an interesting point also that one of the landing sites, that's a Gusev Crater or Columbia Hills, this has actually already been visited by a rover in the past. It was visited by the Spirit rover, which operated between 2004 and 2010. And as some scientists believe that at the landing site there are potential indications of life in the form of a silica-rich structures, chemical structures that somewhat represent biological structures here on Earth. So a certain group of scientists argued for a return to this site, and they made a very compelling case for doing so and exploring it in greater detail. So in the end, there was a considerable discussion about the relative merits, about the relative benefits of an incremental science, which is to say, should we go back to somewhere we've already visited in order to learn more? Or discovery science, should we go somewhere new entirely and discover things about a new part of the a new part of the surface of Mars? And both of these are very compelling arguments. I think in the end it's the promise of discovering something completely new that meant that discovery science won the debate, and we eventually went to Jezero Crater. But certainly it raises the point that there's much more to discover with new technology compared to 15 years ago, what we could discover by revisiting one of the landing sites. I think this is interesting. And indeed, one of the major positive points for Jezero Crater is that it was quite close to one of the other proposed landing sites. So it is conceivable that there is a possibility over the course of the next few years to make an effort at a driving between the two landing sites. And indeed, when presented as a combined mission plan, this received a great deal of support from the community. So this is also one of the things in favor of Jezero, is the potential that in the future, if the rover continues operating for a number of years, it could make its way to a different location on Mars and also explore there. So the rover is a combination of a science, instruments, and technology demonstrations, and it's a highly competitive process also to get your instruments selected for to be on the rover. This is because the mass of instruments that can be taken on the rover is reasonably small. Much of the instrument mass has been taken up by the sampling apparatus. As I said, it's not exclusively science. There are also some engineering and technology demonstrations in preparation for future Mars exploration and potential colonization by people. So one of these instruments is called MOXIE, and this is an instrument that a few weeks ago successfully produced oxygen by a process of splitting carbon dioxide in the Martian atmosphere into carbon monoxide and oxygen. So the idea is that in the future, such technology could be employed for providing oxygen either as a breathable atmosphere for human colonizers of Mars, or indeed as a form of fuel for a future Mars mission. I believe that the volume of oxygen produced by the MOXIE instrument is approximately sufficient to keep a small dog alive and healthy. One of the other instruments, one of the other demonstrations on the rover is a suite of prototype spacesuit materials, so including materials such as Teflon and Vectran, and also the polycarbonate, which in the future may form the visors of a Marstronaut spacesuits. And I believe Caroline will talk a bit more about these because they will be observed by some of the instruments over the coming months and years in order to see how they degrade over time. And the final technology demonstration is perhaps the one that's received the most attention in the press, which is Ingenuity, and this is a small helicopter which has, over the course of the last, I believe, 3 months, performed a number of successful flights, and indeed these are the first controlled flights on another planet. So that's really quite a technological achievement. And over the coming months, it will continue to support some of the science of the mission. At this point, I will hand over to Caroline, and she will speak in a bit more detail about some of the instruments.
Thanks very much, Keyron. Right, so now I've got to try and talk even, and control the screen, which is a bit confusing. So, and just to apologise, I'm going to be looking at the screen that's got the slides on, so I won't be looking at my camera, but so sorry about that. The camera's on a different screen. So as Keyron said, we've actually got a number of instruments and technology demonstrators on the Mars 2020 Perseverance rover. And many of these actually work in conjunction with each other. And so 2 amazing instruments, which are on the sort of, let's say, the head of the rover, are the mast cam and the super cam. And some of the amazing images that we have got back from Mars already come from the mast cam instruments. These can see things quite close to the rover, but they all can also see things in the distance. So they're absolutely fantastic in terms of their sort of depth of field and also the resolution of the images that they can produce. We also have SuperCam, which is fantastic. It's one of the rover's lasers, and it actually shoots out laser beams onto rocks. Then the camera system actually looks at the light that's emitted from that laser beam hitting the rock, and you can actually get chemical information of what that rock's made from. And Keyron will maybe talk about a little bit about some initial data from SuperCam. But also we have on the rover arm, we have a number of instruments and also other devices. We have the SHERLOC instrument, which Keyron and I are heavily involved with. This is a type of instrument which I'll talk a little bit in a bit, but it looks for the minerals and also the chemistry of rocks. And it has a sister instrument called Pixel, which is an X-ray spectrometer, and that also looks for the chemistry of the different rocks and the minerals that the rover encounters. And the SHERLOC actually is a joint instrument. It has a camera system as well, and that is cleverly called Watson. So we often talk about SHERLOC, but it's actually SHERLOC and Watson combined. And one of the things that's really important, I said, these instruments work in conjunction with each other. And this is one of the things that Keyron is looking at, is how you actually combine and correlate the data collected from these different instruments that give you then a combined information on what the rock looks like, its textures, the chemistry of that rock, the different minerals, if there are organics present and things like that. So it's a very, very powerful set of payload instruments that we have to give us this amazing information. So as we said at the beginning, we are heavily involved in the SHERLOC instrument. So this is actually SHERLOC on the arm on the rover on Mars. So you can actually see just in the middle, this is the SHERLOC instrument here. The thing on the left is actually the drilling system. So we can drill into rocks and collect samples that we hope will come back to Earth in about 10 years' time. So as I mentioned, it's a combined instrument, SHERLOC and Watson. Watson can take close-up images of what the rock surface actually looks like. So we get an idea of the textures, if there's different colors, different features. And then the SHERLOC instrument is actually the thing that gives us the chemical and mineralogical information to actually tell us what those rocks are made of, and if there's any evidence of, for example, interesting organic molecules, which could be these indicators of past fossil life on Mars. So how we are involved, one of the ways that we're involved in this SHERLOC instrument is I was at a meeting in 2012 with the principal investigator, so the lead person who was developing the SHERLOC instrument, And at that point, it hadn't actually been selected for the Mars rover, but it was in competition to be put on the next NASA Mars rover. And we were talking about how when you're on Mars, you would actually test to see whether that instrument was working as expected, if everything was working okay, or if there'd been any weird things that you could maybe apply some data corrections, things like that. So I'll be quite honest with you, over a couple of pints in the pub, we were discussing the types of material that you would take, that you would use to test an instrument. And we talked about how we test instruments on Earth in labs. And I said, well, you know, what you really want to do is have your test material, or at least one of your test materials, as similar to the types of rock you would find on Mars. Now, at that point, you know, Keyron's mentioned that the landing site selection is very compelling, also very competitive, and also very compelling arguments for different landing sites. So we didn't really know what type of rocks that we would encounter, but what we do know about Mars is that a type of rock called basalt, which is an igneous rock, is ubiquitous. It's all over Mars, and many of the sediments from that we find on Mars are actually derived from the breakdown of basalt rock. So they are what we call basaltic sediments. So I said, well, why don't we use a basalt as one of the test materials? And then we said, well, hang on a minute, we've got Martian meteorites that are made out of basalt. So these are pieces of the Martian surface that have been blasted off Mars through impact cratering processes over millions of years. We actually have pieces of Mars in the collections on Earth. So I said, well, we've got a really good sample. Why don't you have a piece of that? So lo and behold, a piece of one of the museum's meteorites is now back on the surface of Mars. And so you can see the image on the right. That's my colleague, Trevor Graff at the NASA Johnson Space Center, who actually built this thing called the calibration target. So this is a piece of, it's not an instrument so much, but it's a piece of supporting structure that's on the rover so that we can test the operation of the SHERLOC instrument and the Watson cameras. If we just look at it in a bit more detail, this is what it actually looks like. You can see there are a number of materials on there. So we have a number of things on there. So these have all been specifically chosen to help test how the instrument and the cameras are operating, and also the laser that's very important as part of this instrument. And you can see the Martian meteorite there is slap bang in the middle, in the top of the target there. Keyron mentioned about some of the other materials on the calibration target are actually part of this technology testing. So these are materials that could well be used as part of spacesuits for human explorers of Mars in the next coming decades. So we have a piece of polycarbonate, which is in the bottom left. That's what the astronauts' visors would be made of on the helmets, and then various materials that the actual spacesuits would be made from. And these are going to be regularly monitored during the course of the lifetime of the rover, using the SHERLOC instrument, and to see how those actually stand up to the rigors of the Martian atmosphere. Because, you know, as Keyron mentioned at the beginning, Mars is very dry, it's very cold, there's a very high ultraviolet flux because it doesn't have an atmosphere like we do on Earth to sort of cut out all of this dangerous stuff. There's also gamma rays, cosmic rays, all sorts of nasty things going on the surface of Mars. So we want to make sure that these materials can withstand the rigors of being on Mars for an extended time, as we would hope humans would be in the future. And this is the most up-to-date image that we have that was taken by the Watson camera, and you can see here is the calibration target on the rover on Mars, and you can clearly see already it's getting a bit dusty. Those spacesuit materials are looking a little bit pinky orange. They're getting covered in the Martian dust already, even after 62 sols on the surface of Mars, and this image was taken towards the end of April. So one of the other things I mentioned that's really exciting about the robotic arm is that it has this capability of being able to, it has lots of degrees of freedom, so we can get onto rocks, look at them, get sort of around, have a good look, and it has a capability of actually drilling into the rock, collecting samples, and they get put into the body of the rover, into a thing called the sample cache. This is a sort of it's probably about this big. You can see it has a number of tubes within there. Each of these tubes is about the size of my finger, actually. And these are the tubes that the samples from Mars will be put into by the drilling system, and then they will be stored safely in the rover until such time as the rover drops it off, hopefully to be those samples to be collected by a later mission in about 10 years. And I think I will hand back over to Keyron now, quickly.
Thank you, Caroline. Yes. So, as I mentioned earlier, one of the technology demonstrations that's been up in operation over the last few months is the Ingenuity helicopter. Here you can see it making one of its first flights. Really fascinating stuff. And I think we have two other images here on the slide also. In the lower left, you can see Ingenuity imaging its shadow, and at the top right, you have a very nice close-up image of the helicopter between flights. So this will continue to support science of the mission over the course of the coming months. And indeed, at the moment in the science team, we're considering some of our first data from Jezero gathered by the instruments that Caroline spoke about. So we have beautiful panoramas of the surface of Mars taken by the mast cam camera, and you see in the distance these hills are thought to be fine-grained sediments from the delta. We also have close-up images such as the SuperCam RMI, that stands for Remote Micro Imager. So these are micro images close-up of specific fabrics and textures on the rocks. And we also have chemical data such as the elemental profile here at the bottom, which can help us to understand what kinds of rocks we are looking at. And taking these data together as an ensemble, we can really begin to understand something of the geology and the environment of Jezero crater billions of years in the past. And indeed, we have science team discussions almost every day. At the moment, because we're still in the early stages of the mission, we still have some very fundamental questions. What type of rocks have we identified? We're on the crater floor at the moment, so can we begin to distinguish different geological divisions across the crater floor? Can we begin to understand something of the geological history of Jezero crater? And an important consideration at the moment, which route should the rover take? So at the present time, we're starting on the first science campaign. So planning ahead for the days planning ahead a few days is very important at the moment. So to answer these questions, we have virtual discussions almost every day. These are the science discussions amongst members of the science team, but occasionally ad hoc groups, often called tiger teams, are tasked with investigating a specific question relevant to current or ongoing mission operations. So if we approach a specific type of say sedimentary rock, a group of people with expertise in a sedimentary rocks will be asked, please come together and tell us what we can expect and what we should do to understand this rock as best we can. And we can follow these discussions almost 24 hours because there is a dedicated website. As you can imagine, there are people working on the mission from all around the globe. So if you wake up at 6 o'clock, you will definitely find some new thoughts waiting for you to accompany your breakfast. If we could go on to the next Yes. So every day, every sol, there are a group of people working on the mission, and indeed, I won't go through all of these roles in any detail, but it's reasonable to say that there are people planning the route of the rover, people documenting everything observed by the rover, people considering sampling or the targets or the rock targets that we will analyze. So it isn't just one or two people manning the rover at any time. During every shift, there are perhaps several tens of people involved, including always a staff of these roles who will follow the rover operations in the day and will report on what they observe at the end of each day. And it's true also that because of the intensity of the mission, there are many challenges involved. I've put down a few of these here. As I mentioned, there is a difference of approximately 40 minutes between a day on Mars and a day on Earth, and this means every day your working pattern early in the mission, every day your working pattern changes by approximately 40 minutes. This can be somewhat challenging to keep a track of at times. Also, since the majority of the team is in the USA, we often find ourselves working into the evening or into the early hours of the morning, or going to bed after operations as the sun rises. And on that note, it's also something to note, and this is something that certainly affects me. It's an extremely interesting thing to be working on, and it's very easy to become overwhelmed with meetings and responsibilities, because it's hard to say no to this kind of thing when so many discoveries are made on a day-to-day basis. It's also true that normally we would be located in the same place. We would be in JPL in Pasadena, close to Los Angeles. But due to pandemic times, all of the operations, mostly for the science team, are being done remotely, and only a crew of engineers are actually on site. And I'll also make the final point here that one of the main challenges is that there are people from many disciplines and with many viewpoints working here on the mission and on the data. So an open mind and a willingness to challenge your own ideas and your own hypotheses is necessary, because as more and more data come in, we have continuous reinterpretation of our results.
Okay, thank you, Keyron. So we'll go on to now talking a little bit about a very important part of the rover's mission, which is this sample return to collect samples on Mars and bring them back to Earth in about 10 years' time. So we've discussed that what we're trying to do at the Jezero crater is to look at its geological environment, look at the geological diversity, look at the types of chemistry that is recorded in the rocks that we find at Jezero crater, and also crucially look for the evidence of organic molecules, because depending on what those organic molecules are and the way they are preserved in the rocks can give us a very good idea of whether those are organics that were generated through biological processes or just through, let's say, normal chemistry processes, so no biology involved. So the rover is going to be collecting about 30 samples of rock. We are hopefully looking for different types of rocks, so sedimentary rocks, igneous rocks, so volcanic rocks, and also some of the dust as well. That's very important for human exploration, because that dust could actually be hazardous for humans going to Mars. And we're also going to be looking at, when we're collecting those rocks, actually really investigating what those rocks are like. Do we actually want to collect them? And when we collect them, will we have a good idea of what we're expecting when they come back to Earth? So as we've been saying, this mission is a life detection mission. It's looking for the evidence of past life. And we really think with the suite of instruments that we have on the rover and its capability, we've got the best chance of actually answering that really key question: was there ever life on Mars? One of the problems, though, with the rover is that even though the instruments are absolutely fantastic and they are some of the best instruments, most technologically advanced instruments that we've ever sent to Mars, there is always a limitation of when you send an instrument or a rover to Mars. What you can send is limited by its weight, how much energy it takes up, and also things like that. So there's a lot of engineering constraints on choosing this payload. And also, because we don't always get the fidelity of the types of analyses that we can do on Earth, there's always some sort of ambiguity in the results. You know, that feature that you've seen using this amazing instrument, is it actually what you think it is? You know, you really need to, we call it ground truth, have a look at that on Earth. And so that's why we have to actually get these samples back on Earth to actually really dig into them and use the whole suite of instrument capabilities that we have in labs, like we have at the museum, but also all around the world. So this is the current proposal. It's called the mission architecture for the Mars sample return mission. It's very complicated. It involves multiple different spacecraft provided by NASA and the European Space Agency that's going to do lots of things. This is quite a complicated slide. I'll try and whiz through. So we're in the first phase of this mission architecture, this mission campaign. So where we have the rover on Mars, exploring around Jezero, looking at rocks, collecting rocks, and then hopefully dropping them off somewhere. In 2026, there is a joint NASA and ESA mission to send something called the Sample Fetch Rover, which is actually at the moment is going to be led by Airbus in Stevenage. So that's very good for UK engineering. That will be the rover that will land on Mars and then go and find the samples that have been deposited by the Perseverance rover. And then in 2029, another mission has gone, and that will actually blast those samples from the surface of Mars into orbit, where it will be collected by a satellite that's waiting to collect those samples. And then in 2031, those samples hopefully will land safely in the Utah desert. Slightly worrying with this ESA diagram that we've had a bit of a laugh about. For some reason, the sample canisters seem to be in the ocean. We don't want that to happen at all, but they will hopefully come back to Earth in 2031, ready for all of the fun sample science to actually begin. So as I mentioned, you know, we really need to interrogate what these samples are made from, what we think we've seen with the rover instruments. Are those actually real features? Are those real chemistries? Are those real textures that might be little, you know, fossilized little tiny bacteria, things like that? And we really need to use some, you know, instruments that take up a size of a whole room that you could just never miniaturize enough to be able to go on the rover. So we'd be using things like transmission electron microscopes, scanning electron microscopes. Microtomography is a new technique that we now use in earth sciences. So this is the same technology that if you ever unfortunately had to have a CT scan of your body, we can now do that on rocks, and so we can see inside rocks using X-rays. So all of this very sort of cutting edge equipment that we have in labs that we just simply can't send, unfortunately, to Mars, and we'll never be able to do that. So we have to bring the samples back to us. Now, one of the things that's very important to consider, you know, we've emphasized how this is a mission that may well detect evidence of past life on Mars and bring back rocks that have past life on Mars. Now, this is taken very seriously. In the 1960s, prior to the Apollo missions, many of the nations got together and said, well, what happens if we actually bring back something from another planet that's alive and causes problems on Earth? Or indeed, what happens if we go to somewhere that has the conditions for life and we take life with us and accidentally contaminate that place? So the United Nations had many working groups with many eminent scientists from the time. And this is actually now in international law under the United Nations Outer Space Treaty. And Article 9 is the pertinent one here. I've highlighted the sort of section there, but this is basically where we say we don't take anything to a place of interest with us. We don't want to take any bugs on our rovers or our satellites. And similarly, we don't want to bring back anything that could cause problems for the Earth. And so this is called planetary protection in its broadest sense. So just taking that that sort of bit from the Article 9 of the Outer Space Treaty. So this is the moon. It was focused on the moon at the time because the Apollo missions were coming up, but it's also for every other body within our solar system. So what we call forward contamination is where we send a rover to Mars. It has loads of, I don't know, COVID on it or Ebola or other nasties, and we contaminate that place. That's called forward contamination. We don't want to do that. But similarly, we don't want to bring anything back from these places on a sample return mission that could potentially cause problems for our own biosphere. So we don't want to bring any nasties back with us from those places if there are any nasties there. So what we really want to do is, it came from outer space. Do we want the alien death bugs coming back? No, we don't. And so we actually have many people working on this. NASA has a very large team in the Planetary Protection Office looking at these issues. ESA also has a large team, and all of the national space agencies have various people working on this to avoid that situation of doing something that we don't want to do. Now, it sounds a bit science fiction, and in fact there is a very good book and a very good film. Some of you may have heard of this or read it yourselves. The Andromeda Strain was written by Michael Crichton in 1969. In fact, it was his first book, and it was a great hit at the time. And it was made into a film in 1971. There's also a film from, I think, about 2012. That's on Netflix. Don't watch it, it's rubbish. But the first one is really, really good. And I love both the book and the film. In fact, I actually read the book first when I was about 11 because my dad had a copy. And I find it quite amazing that I remember that book vividly. I've read it many times since, and I'm now actually working in this area. But I just want to show you the trailer for the film because it actually gives you an idea of what was being discussed at the time. And the point is, it is still relevant today, and we are still discussing the same things today. So hopefully this will work. And I'll put my microphone on so you can, or off, sorry, so you can hear the.
Now don't be scared. I'm a doctor.
Don't know why that stopped.
Where am I? A special laboratory in Nevada. We brought you here. You're sick.
In a true biological crisis, which our exploration of space could bring about, the present lunar receiving laboratory might prove inadequate. I therefore urge the establishment of a facility to deal specifically with an extraterrestrial form of life.
Seems to me, General, Dr. Stone put one over on you. In fact, he made us all think his wildfire lab could handle any contamination from outer space.
Isolate and identify. Good God.
It's no accident. I suspect they were looking for the ultimate biological weapon.
You could change everything.
It's crazy. I didn't know buzzards fly at night.
Buzzards only come when something's dead.
Vandal Decker to Cable 1, what's happening?
We see bodies. Lots of them.
These people were cut down in mid-stride.
Everybody's dead! You did it!
I recommend calling a wildfire alert.
All members of your team have been cleared and are now being called in.
If things get out of control, even you can't work miracles.
Grandpa, there's a car and they got guns.
What's going on?
This communication is being monitored.
Never believed this could really happen. You knew, Stone. You knew it!
I didn't think it possible.
I wish I could believe you.
Whether you do or not, the only important thing now is to find the antidote. Even with a microscope, they're blind.
I'm turning off the oxygen.
Experiment with your own life, damn it. I'm scared. Oh, Lord, I'm scared.
So hopefully that's given you a flavour of what we're doing. I do have to emphasise at this point that the Mars Sample Return mission is not to bring back life to create the ultimate bioweapon. That's part of the story. But some of the principles and some of the things that are discussed within the book and is gone into the film, as I said, even though it's now, what, 40 plus years old, 50 plus years old, it's still actually scarily sort of accurate in some ways to what we're doing now. So as I said, this is something that is taken extraordinarily seriously by the international community. And there have been many studies over the years looking at how we will be able to bring back samples from Mars and indeed other places in the solar system and not have a situation like the Andromeda strain. So I really just want to emphasize, that the intellectual effort and time that's going on with across the board of many different fields, biologists and biomedical scientists, geologists, chemists, are all working very hard to make sure that we are abiding by those principles that were initially outlaid in the UN Outer Space Treaty in the 1960s. So there's a number of studies again ongoing. So even though the Perseverance rover is going about its business on Mars and already producing some excellent results, we're also planning for how we work on the samples when they come back in the early 2030s. I've actually been part of two of those studies, I've just realized. And so again, this is work that is ongoing. We're not sitting sort of waiting, twiddling our thumbs for those samples to come back. We're working very hard. And I really want to emphasize that these are international working groups. It's not just Americans, it's not just Europeans. We're working together very, very well to look at some of these issues that are still outstanding so that we can maximize the scientific return from the samples when they're returned from Mars. So, Perseverance is a new mission. There's new technology on there. There's new ways of doing things, but it is the latest step of our expanded and our long history of exploring Mars using many different rovers, landers, and orbiters. And so we are not sort of doing things new. We are using that legacy and that heritage to, as Keyron said, to do actually some discovery science. So although we're basing a lot of what we are doing on previous missions, there's a lot of new things as well. So as I said, the payload on the rover is fantastic. It's got some new types of instruments on there. So the SHERLOC instrument that Keyron and I are involved in, that type of instrument has never gone to Mars before. And we also have some amazing cameras and other imaging systems to be able to really look at those rocks and the samples in very much close-up detail. And of course, we're going to be able to collect samples of those rocks and bring them back to Earth in the next decade. So really, this is like our robot geologist on Mars. It really is as good as we've ever had to having like a geologist on Mars. So as geologists, Keyron and I are very excited to be able to work with this amazing rover and all of our colleagues at NASA and around the world operating the rover and planning what it's going to go and do. We've got a lot of time ahead of us. Keyron's mentioned that we are talking years of this mission. We won't get the samples back until about 2031. We've got a lot to do. We've got a lot of things to think about, and also some still outstanding issues that we've still got to sort out. And I think that's it. So thank you ever so much, everybody. Thank you very much, Rochelle, for inviting us and eventually battling through the museum email firewall. Right. And I realise we've sort of whittled on for quite a while, but yes, hopefully you found it interesting. Oh, yes. And very happy if you've got time. I mean, you've all got busy lives and things to do, but if you've got time and you want to, we'd be happy to take any questions or comments that you have.
Thank you very much indeed. Thank you very much indeed, Caroline, Keyron. A truly remarkable project and also presentation this evening. It's immensely exciting. So, do we have any questions for Caroline or Keyron? Oh, David would like to. Gould would like to ask a question. Would you like to unmute yourself, David? Oh. And then Mel's next then. David, you?
don't know if you see it.
The internet's full of supposed proof that the moon landings in 1969 were faked and never happened. Do you get the same accusations for your Mars project?
Funnily enough, no, I don't think anyone's ever actually accused us of faking the various Mars landers. And it's quite interesting that, you know, there is, as you say, there is all of this conspiracy theories about the moon. One of my best friends actually is a chap called Ryan Ziegler, who's the Apollo sample curator. And if ever you want to wind him up, you just have to ask him about, oh, come on, all of those rocks you've got in your collection at Johnson Space Center, oh, you've just made those up, haven't you? I mean, I can assure you that those moon landings were not faked. There's various chemical evidence from the rocks that we have on the moon that we wouldn't have been able to make features of those, you know, in labs on Earth. So yeah, yes, the moon landing conspiracy theories is one that amuses me. But no, I've never seen anything about the Mars landings being faked. I mean, you do see stuff on the internet where people think that that some of the images from the orbiters or even images from the rovers show things that look like alien artifacts. That's quite a popular one. But yeah, certainly nobody's ever, that I know of, has ever accused any of the Mars missions as being faked.
Oh, thanks very much. Mel up next.
Thank you for a fascinating talk. You referred to, in one of your samples, that the Martian meteorite is one of your, at the time when these Martian meteorites were first discovered and talked about, they were very controversial. I know Patrick Moore was very skeptical about their origins. Can you confirm that these are actually meteorites from Mars? I mean, how do you nail it, as it were?
Yeah, okay, that's a great question, and you're right. There was a lot of controversy about the origin of these Martian meteorites. There are a number of features within those rocks. So the minerals that are in there, the chemistry of those minerals, and the way those minerals are put together that show that those rocks had to be from a place in the solar system that had active igneous activity. And the only places that we know of that would be the Moon and Earth and Mars. Now, we have samples from the Moon, which were collected by the Apollo astronauts. Just under 400 kilograms of lunar rocks were collected. When you compare the composition of those to the Martian rocks, they're similar in some ways, but they're also very, very distinctly different. And that means they had to be from different places. So there was various bits of evidence sort of coming through as more Martian meteorites were discovered, and also as the techniques to analyze them got better and better. But the real clinching piece of evidence actually came about in the early 1980s. So we mentioned the Viking landers. Those were the first landers to go to Mars. Late 1960s. And one of the things that the Viking landers did when they were on Mars was, for the first time, actually measure the composition of Mars's atmosphere. So Mars has a very tenuous atmosphere, but it does have an atmosphere, and it's very unlike Earth's atmosphere. For example, there's very little oxygen there. So one of the things that can happen when a rock forms, or indeed gets impacted, is that rock can actually trap atmosphere that is surrounding that rock. And so there was a Martian meteorite discovered in 1979 in Antarctica. At that point, they weren't called Martian meteorites, they were called SNC meteorites, because their origin was still under debate, although by that point people thought Mars was probably the prime candidate. So that rock was collected in 1979, and then it was only in 1983 that we had instruments sensitive enough to measure what we call trapped gases or trapped atmosphere. This is tiny, tiny volumes of gas which are actually trapped within the minerals. And when the composition of that gas was analysed, lo and behold, it had exactly the same composition as the Martian atmosphere that had been measured about, by that point, 5 or 6 years previously by the Viking landers. So that was really the sort of icing on the cake. The debate was finished then, because there's no other way you could get atmosphere with Mars's composition in a rock if it wasn't from Mars.
That's it. Thank you very much.
Thank you.
Thank you.
So Jeff Wilson next then. Right, so unmute yourself, Jeff, please.
Yes, hello. Excellent talk tonight. I just wanted to know how the helicopter manages to fly if there's no atmosphere, or if the atmosphere is very thin. How did it manage to get off the ground without any sort of rocket launchers?
No, I think that there are two major factors in play here. first is that the helicopter is extremely lightweight, and a second is that the speed of rotation of the helicopter propeller is many times faster than the speed of rotation required for an object of equivalent mass here on Earth. So these two things combined enabled the helicopter to take off and perform a flight of up to several tens of seconds in length. Over the course of the coming months, it will attempt a slightly longer and more complex flights, and we'll see how those go. I believe until September or October it will remain in operation. But it's the combination of a very lightweight construction and an extremely high revolution rate of the helicopter propellers that enable it to maintain flight.
Thank you.
Thank you very much. Have we got Jeff Wilson?
Yeah.
Thank you.
Thanks for the talk, guys. Very interesting. Why is red the predominant colour?
Keyron, do you want to do that one?
I'll take this one. It's because of the strong effects of oxidation of the iron at the surface of Mars. So the igneous rocks and the sediments and the dusts at the surface of Mars are extremely rich in iron relative to Earth. So over the course of billions of years, a deep iron oxidation has affected the surface millimeters of the whole planet of Mars. However, if you look, for example, at boreholes or abrasions made by the Curiosity rover, you'll see that after a few millimeters of abrasion, the rock beneath is grey. So it is a superficial effect, but it's because of the oxidation of iron.
Thank you.
Yeah. Thank you very much. Shana, would you like to ask your question? You have to unmute yourself, Shana. Shana? No? Okay, go on to Roy next, please.
Thank you, Keyron and Caroline, for that splendid talk and those amazing images. I'm just wondering what you envisage as being the benefits for us on Earth from all the research that's been going on.
Oh, no.
Good question. I'll maybe Keyron can start, and then maybe I'll add if he hasn't covered that, I think.
Of course, yes. I mean, I'll start with the fact that I think discovery science has always been and will always be of value to human understanding, knowing what else is in the solar system and how, and understanding more about our own place in the solar system. I think that this is invaluable from a knowledge perspective. Also from the view of technology, many of the miniaturized instruments that are made for application to Mars rovers and more broadly to space missions find technological applications here on here on Earth also. So there are technological applications developed for Mars that inevitably become highly useful for us here on Earth also. I don't know if you want to add anything, Caroline?
Well, yes, I can give an example. So it's not an instrument that's on the Perseverance rover, but an example of that application of miniaturizing technology and how it can benefit is the Open University, where I did my PhD, actually has international expertise in developing miniaturized instruments based on amazing lab instruments that they've actually developed. And they had an instrument on the, you may remember there was a European Space Agency mission to a comet, which I can never remember the name. It's got an unpronounceable Russian name, something like Cheremensky. I can't say it anyway. We used to call it 67P, it's much easier. Anyway, so that was based on, as I said, an amazing instrument that I actually used during my PhD that literally takes up the size of a lab, and they were able to miniaturize that instrument down so it's about the size of a shoebox. And one of the things that has been spun out of that technology is a way that you can actually take samples of human breath. So you breathe into a pipe and it goes through and the instrument measures it, and you can actually detect whether somebody has tuberculosis. Now, the traditional way of obviously testing to see if somebody has TB is to do one of those tests, see if the thing comes up, and then you get the jab if you test positive for TB. Now, that's obviously quite easy to do in developed countries, but it's very difficult to do in developing countries where the time between the test being taken and the results coming back takes a long time. You want to be doing these testing quickly and inoculating people who need those inoculations and then move on to the next place. And so this technology has been used now to do portable TB detecting units that can be taken out to inaccessible regions or other places where doing the sort of traditional lab tests is just unfeasible. So that's a direct benefit of the sort of space industry and the technology development for space missions with a tangible benefit for human health on the planet.
Thank you so much.
That's lovely. Thank you. Over to Eva now.
Thank you very much for the amazing talk. With this wonderful spectroscopy analysis, have you found any new element or new isotope or new rock which we didn't know on Earth?
So we do have on Mars and also in meteorites as well, we do have some minerals that you either don't get on Earth or you only get in very, very unusual and sort of rare circumstances. But in terms of isotopes and elements, it's exactly what you find on Earth. They're just there in different abundances. So you might find certain isotopes of elements on Mars or in meteorites that, again, you just simply don't find on Earth because we don't have the right types of rocks to record those isotopic compositions or indeed minerals. And in fact, it's one of the ways that we actually use to identify some materials as being extraterrestrial is looking for those unusual isotopic signatures or unusual minerals within those rocks that, again, you just simply don't get anywhere else. And that attests to the fact that everywhere in space has its own environment, and those different environments are recorded in that chemical record within the rocks, whether that be isotopic signatures, elements, trace element abundances, and the ways that those elements are actually put together within the rock.
Thank you very much.
That's lovely. Over to Martin now for your question.
Oh, good evening. What fascinating lives you both lead. Must be amazing to wake up in the morning and to do what you're doing. Must be absolutely fascinating. I've got about 5 questions, but I'm not. I can't ask them all. So what I'm going to do is I'm going to combine one question, and if I may, I can ask a separate question. The first question is: we talked about the red planet and the reason that it's red. We all know that Mars is red, and you've given the explanation as to why. But what colour is the Martian sky? And is there a Martian day and night? that's the first question. The second question is what data, I know the mission is in its early stages, but what data so far has been sent back that has been completely unexpected and a revelation to you both?
Well, I might hand both of those over to Keyron, and then I might actually just go and grab a glass of water because I'm getting a bit of a hoarse throat. So, I'll hand them over to Keyron, and so I'm going to disappear, but I'll be back in a second. But I can still hear you, so don't say anything inappropriate.
I'll start off with a question too, because this is the kind of thing I actively work with on a day-to-day basis at the moment while following mission operations. So at the moment we've had data back in the form of images. We've had data back in the form of very close-up microscale images, and we've had data back in the form of a chemistry, so a elemental chemistry or a molecular chemistry. At the moment, some of the major unexpected finds have been related to the distribution of a very fine-grained sediments, and certainly in the distance of some of the images, very similar to the one here, but in the distance of many of the images, we have these very fine-grained hill-like sediments, which we showed in a few of the earlier photographs. These look very different from our expectations based on orbital images. We also have, for example, and as has been released in some of the images, beautiful bedded sediments, which really help to confirm the origin of the delta as a delta. These kinds of images can only be obtained at the surface. From orbit, we see the broad structure of the region, which we call the geomorphology of the region. But it's really only at the surface when you can see cross sections through outcrops of rock. At this stage, you can really begin to understand some of the geological complexity. So we have seen some unexpected complexity in certain rocks related to the delta. I think unexpected complexity, which is very, very promising for the preservation of a fine-grained sediments which may preserve organic materials. I think those have been the major unexpected, or at least pleasant surprise discoveries observed so far. Question one was the color of the Martian sky. So from the surface of Mars, the images we've shown are very carefully color calibrated. So the colors we see in these images are reasonably true to the colors that would be seen on Mars. So in the images, the hues of the sky seen are reasonably representative of what we would also see.
Thanks very much. Right, we're going to go on to Paul now. Paul Lippman.
Good evening. Thank you for explaining something so complex into much simpler terms. My question is, what are the parameters of temperature on Mars, and how do they affect the technology?
Good question.
Oh, Caroline, you are muted.
That's, I think, the first time I've done that today.
Oh,
Yes, so there is quite a temperature range on Mars. So at warmest, it goes up to probably about 18, 20 degrees, something like that C. So actually quite similar probably to the temperature on Earth today. But then it gets very, very cold as well. And there are some parts of Mars that are what we call in sort of permanently shadowed regions. So these are down in the bottoms of craters where sunlight just simply never gets to. And those are sort of almost absolute freezing temperatures, so very, very cold. Keyron, anything to add on that?
No, I don't have anything to add on that. No.
But you're absolutely right. That has a big effect on the technology of the rover. So one of the things that this rover has is its power is from a small radioisotope thermal generator, an RTG. So it actually uses nuclear power. And one of the things that nuclear power source is actually keeps the rover warm when it's actually getting very, very cold. And that's one of the issues with rovers that are powered by solar panels, is that actually the solar panels, well, two issues. The solar panels can get covered up with this ubiquitous dust that is in the Martian, is on Mars and is in the Martian atmosphere. So that actually reduces the efficiency of those solar panels over time. So actually then we hope for a nice big windstorm to blow all of that dust off, and then that dust builds up again. But also as well is the power load on those rovers and those landers that are solar powered is much more, it can fluctuate because of this issue with the efficiency of the solar cells. And sometimes we think that with the Mars exploration rovers, Spirit and Opportunity, one of the reasons why they had to basically, they stopped working was because the rover was not getting enough energy from its solar cells to keep itself warm, and it froze.
Oh, thanks very much. Irene, would you like to ask your question?
Hi, hello. Very, very fascinating. I want to ask two questions. One, how does the planet lose its atmosphere? Or say, how did Mars lose its atmosphere? And the other question, I believe that trees can grow there. So if we grew enough trees to increase the oxygen, would life be possible?
I can take those, or do you want to do it, Keyron?
You could take those, Caroline. Yes.
Okay, so how Mars has lost its atmosphere. So one of the things with Mars is we think that unlike the Earth, it has a very, or it had and has a very small metallic core. Now, one of the things that makes our Earth habitable is that we have this amazing thing called the magnetosphere, which is this magnetic shield caused by the rotation of our still molten iron core, which actually protects our Earth from cosmic radiation and solar wind. And unfortunately, Mars doesn't have a magnetosphere. And actually, we think that Mars lost its magnetosphere in about the first billion years of its life. So Mars doesn't have that nice protective magnetic field around it to protect it from the rigors of the solar wind, other cosmic rays coming in from galactic cosmic rays and other things like that. And the action of that very harsh radiation environment physically stripped away the Martian atmosphere that was there initially. So probably for the last 3 billion years or so, maybe 2.5 billion years, Mars hasn't had that nice protective atmosphere to keep things nice like we have on Earth. With regards to trees growing on Mars, people have tried to recreate as far as possible the types of soil that we find on Mars. So we call it regolith when it's on other planets and asteroids in labs on Earth to see what they can grow in it and what can happily live in it. Also, as well, we mentioned the MOXIE instrument, whether you can use that soil, for example, to build things from or to break it down to get at things you need for human explorers. So we do know that the Martian soil probably can support some growing of, let's say, agricultural stuff. I don't know. I've never heard about trees being grown in Martian soil, I'll be honest with you. So I couldn't really comment on trees growing on Mars. But of course, the major thing is that Mars is very cold. It is very dry. It has this very inhospitable environment because it doesn't have its nice protective atmosphere. So I think if you were to plant trees out in the open on Mars, they wouldn't last for very long. And certainly not long enough to produce oxygen to then oxygenate the atmosphere. And then even if you did, it would get stripped away very quickly by the harsh solar wind because there's no magnetosphere.
Thank you.
Thank you very much. And the last question goes to Gillian Walker. Would you like to unmute yourself then? Can you unmute?
It's actually my partner, Bernie, who posed the question. So
yeah, sure. Go ahead. Last question.
Strictly speaking, geologists study the rocks on Earth from the derivation of the word geology. What should we call people who study the rocks on Mars?
Oh, that's a very good question. Yeah.
Marsists, I don't know. Yeah, I mean, we are most of us who obviously study the geology of different bodies in the solar system. We still call ourselves geologists, but often we do then sort of clarify it by saying we are planetary geologists or planetary scientists. But actually, many of the geologists who study lunar samples and the moon call themselves lunatics.
Thank you.
Thank you very much. Well, on behalf of everybody, I want to say thank you so much for your superb presentation this evening. It's been truly remarkable. And now I think everyone realised why I've been so persistent in the last few months. And it's been amazing. And we've looked in wonderment really at the landing. And of course, we've got this project ourselves now to look at for the next 10 years. So I hope perhaps we can ask you back next year and then you'll be able to talk to us about any developments. So it'll be brilliant, every year that we can, you can keep us posted. But thank you so much for giving up your time. It's been absolutely wonderful. And thank you too.
Thank you very much for inviting.
That's right, great pleasure. And also to the our members who asked such interesting questions. And special thanks to Morris, our technical director. Thank you so much. It was marvelous.
Drop off the call, everyone. I really would urge you to have a look at the Mars Perseverance website. If you just do a Google for Mars Perseverance or Mars 2020, it will take you straight to the mission website. NASA spend an awful lot of money and time and effort on these websites for public consumption, and they are absolutely fantastic. And I can assure you that the images that we get back from the rover that we can see, it is only a few hours later before those images are actually released on the public website. So I am obviously looking at it regularly, as is Keyron. It's really good. There's loads of interesting stuff on there, and you can actually have a look at the images as they sort of get released on a daily basis. So there's always new things to have a look at, and they have an image of the week, for example, and things like that. So I really would recommend, if you've got a spare 10 minutes, have a look and see what's going on.
Thank you very much. I think we'll all become groupies now. So
Groupies.
Thank you so much.
Thank you so much.
Thank you.
Thank you. That was really, really interesting. Really interesting. Thank you for organising it.
It's all right. Great pleasure.
Haven't seen the little green men.
Surely little red men.
Waiting to see them. Not sure whether we will.
We'll keep a lookout. Yes.
Yeah, that's right.
Yeah. A real privilege to hear you. Thank you.
Yes. Yes, it's been wonderful. Thank you so much.
Thank you so much. Thank you.
Well, it was nice to meet you all, and hope you have
it was.
Rest of your
we'll invite you back now.
Yeah. Okie dokie. Well, I'm gonna sign off.
Yes, thank you so much, Caroline.
Thank you very much. Thank you.
And Keyron.
Thank you. Thank you all. Yes.
Thank you.
Thank
you again.
Thank you, Rochelle.
Yeah, thank you. No, pleasure. Thanks.
Bye.
Bye now.
Good night.
Night, everybody.
Night. Night.
Night. Thanks.
system is closing down. Processing needs to happen.
Closing down.
Very
Yeah.
nice.
The slow goodbye.
No, it's going to be a quick goodbye. It's going now.
It's going off, is it? Okay then.
Yeah. Sorry, it's 10 o'clock. I've still got a load of processing to do for
Oh,
this.
okay.
So, if you see me in the morning with matchsticks in my eyes, you know the reason why.
Yeah, I know what you mean. Yeah. Okay, good to see
take
you.
care. Well done,
Take
Rochelle,
care.
for arranging it.
That's right.